Hello, we are PCz Rover team from the Częstochowa University of Technology in Poland, and this is our new rover, Beaver. We have been one of Poland's most accomplished rover teams for over a decade, and we are proud to represent our university on the international stage. Our greatest achievement came in 2018, when we won the University Rover Challenge in Utah, USA, one of the world's most prestigious student robotics competitions, with our rover Modernity 2, making us one of very few European teams to ever claim the top prize. Over the years, we've consistently proven ourselves on the international stage, third place at URC 2017, fourth place at URC 2019, and multiple top 15 finishes in both URC and ERC competitions with our successive rovers. Now, in 2026, we return to competition with Beaver, a fully redesigned rover built for the Anatolian Rover Challenge, representing the next chapter in our team's pursuit of engineering excellence. Our entire design, manufacturing, and testing process takes place on the campus of the university. We are lucky to have access to the university's workshops, laboratories, and engineering facilities, where every component of Beaver was designed, built, and refined by our team members. From the first CAD sketches to the final field tests, everything happens under one roof, allowing us to move quickly, iterate fast, and work closely together as a team. Beaver moves on a 6-wheeled rocker-bogie suspension system, the same architecture used by NASA's Curiosity and Perseverance Mars rovers. Each side of the chassis features 3 wheels connected through a series of articulated rocker and bogie arms, all linked by a central stabilizer bar running across the top of the rover. The system is entirely passive. No motors, no sensors, no extra control logic. Pure geometry and gravity do the work, keeping all 6 wheels in contact with the ground at all times. Beaver weighs approximately 45 kilograms and measures 125 by 97 by 125 centimeters. We chose rocker bogie because the Anatolian Rover Challenge demands precision and reliability over speed, navigating craters, loose soil, gravel, and slopes of up to 30 degrees. This system handles all of that with zero additional complexity. During field tests around our city, Beaver consistently performed on loose soil, compacted gravel, and uneven terrain, giving us full confidence heading into the science mission, night mission, and collaboration mission at ARC 2026. Beaver's electronics are built around 5 custom-designed PCBs, each dedicated to a specific role: power management, manipulator control, science payload, CAN bus interface, and antenna mast. The brain of the system is an NVIDIA Jetson Orin Nano for perception. We use a Z stereo camera paired with an IMU. The Z handles depth sensing, obstacle avoidance, and Aruco marker detection, all in one unit. 6 maker-base VESC mini ESCs drive the wheels over CAN bus, 1 controller per wheel. On the power side, 3 SLS LiPo batteries in parallel give us 15,000 mAh and around 333 watt-hours at 22 volts. That's roughly 2 hours of standard operation. The system is protected by a 125 amp fuse and a solid-state relay tied to an emergency stop button. A 3-color activity light shows the rover's state at all times: green for remote, yellow for autonomous, red for disarmed. Why these choices? The Jetson outperforms typical single-board computers by a wide margin when it comes to real-time AI and computer vision. The Z camera consolidates depth sensing and marker detection into one sensor, keeping the architecture clean. And the custom PCBs cut out any redundant components, which directly reduces mass. For ARC'26, the Jetson runs marker detection for autonomous navigation through airlocks and lava tubes. The STM32-based boards give us precise actuator control for manipulation tasks, and our ESP32 active antenna mast keeps the RF link stable across the full competition field. That's Beaver's electronics, purpose-built, fully custom, competition-ready. Beaver's manipulation system is one of the most critical and complex subsystems on the rover, and one we are most proud of. At its core is a fully custom 6-degree of freedom robotic arm, 6 degrees of freedom, giving us the complete range of motion required to handle precise multi-step tasks across every ARC 2026 mission scenario. The arm is driven by CubeMars MAB brushless DC actuators, a deliberate and carefully considered choice. Unlike conventional servo-based solutions, brushless motors deliver significantly higher torque output, greater positional precision, and far superior long-term reliability under repeated load cycles. The integrated motor controllers built into each actuator reduce wiring complexity, keeping the entire system clean, maintainable, and resistant to failure in the field. The trade-offs, higher power consumption and a more demanding tuning and configuration process, were fully accepted by the team because at competition level, performance and reliability must come first. The arms control architecture draws direct inspiration from humanoid robotics. We applied the same joint coordination strategies used in advanced bipedal robotic systems to achieve smooth, fluid, and reliable multi-axis movement, even during the most precise and time-critical task sequences imaginable. With a maximum reach of 1,100 millimeters and a payload capacity of 6 kilograms, the arm operates comfortably across the full range of ARC mission requirements, from close-range manipulation on instrument panels to extended-reach sample collection on the Martian surface. The total arm mass is approximately 10 kilograms, carefully balanced to maintain rover stability during dynamic operation. What truly sets our arm apart is the modular end effector system. Interchangeable jaws can be swapped rapidly between missions without any major hardware changes, making the arm instantly adaptable to completely different task profiles. For the collaboration mission, we developed a dedicated beak-shaped end effector, purpose-engineered specifically for precise keypad input on instrument panels, a task that demands repeatable millimeter-level accuracy. In the night mission, the arm closes valves, connects pipes, and handles repair tools, all in low visibility conditions. In the collaboration mission, it operates control panels, replaces components, and cleans solar panels. In the science mission, it collects regolith samples directly from the surface and delivers them to the onboard science payload for analysis. One arm, 6 degrees of freedom, fully modular, every mission, fully covered. Beaver's science payload is built for one purpose: collecting, storing, and analyzing samples entirely in the field. Samples are gathered directly from the surface using the manipulator arm's gripper jaws and stored in a revolver-style multi-chamber container, allowing multiple collections in a single 30-minute run without returning to base. The container is sealed inside a servo-actuated safe box, keeping every sample uncontaminated from the moment of collection through delivery to the judges. Onboard analysis is performed using an RGB spectrophotometer, which measures the optical properties of regolith mixed with distilled water, dispensed automatically by onboard pumps, enabling quantitative mineralogical analysis directly in the field. No laboratory required. The entire system is designed to meet every ARC 2026 science mission requirement: sealed samples, multiple collection points, and real onboard data, all within the time limit. Beaver communicates with our ground station over a dual-band wireless link using Ubiquiti rocket access points, operating at both 2.4 GHz and 5 GHz with a maximum range of 1,000 meters, far exceeding the 40-meter ARC competition field. All data is transmitted via UDP protocol, keeping latency minimal and rover response instant. On the ground, our operator uses a laptop running a fully custom-built control panel written in C++, developed entirely in-house, with 2 joysticks for simultaneous independent control of both the drive system and the manipulator arm. 5 cameras mounted on BeaverFeed live video directly to the operator, covering the front, rear, arm workspace, and science payload area, providing complete situational awareness without any line of sight to the rover. The dual-band setup also gives us the flexibility to switch frequencies and avoid RF interference from other teams, critical when multiple rovers operate on the same field at the same time. Beaver's software is built entirely in-house, every single line of code written by our team. The brain of the rover is an NVIDIA Jetson Orin Nano running Ubuntu 22.04 and a fully custom ROS 2 Humble stack. No third-party packages, complete control over every layer, from low-level hardware drivers to high-level mission logic. Every onboard board, manipulator control, science payload, and communication runs firmware developed and tested entirely by us, refined through countless test cycles to ensure reliability in the field. Autonomous navigation is powered by a ZD stereo camera for depth perception and obstacle avoidance, combined with an RTK GPS for centimeter-level positioning precision. The system reliably detects ARUCO markers and meets all ARC 2026 autonomy requirements: fully autonomous, fully custom, fully reliable. That's Beaver, designed, built, and tested entirely by us at the Częstochowa University of Technology. We would like to thank all of our sponsors and supporters whose generosity made this project possible. We couldn't have done it without you. We are PCz Rover team, and we can't wait to see you at ARC 2026.